speak on vertex algebra and associated varieties. Professor Anima.
So first of all, I would like to thank the organizers for the invitation and also all supports for organizing the visit. For me as well, it's my first time in India, so it's a very great pleasure to be there, so thanks. Yeah, so my lectures will be about vertex algebras. So let me start by saying a few words about motivations, so historical motivations to study them and present the plan of my lectures. So vertex algebras are algebraic structures introduced by Borchert. So let's say that they are algebraic structures. So of course, at some point, we will see a definition introduced by Borchert. So you can see them as a powerful tool in representation theory. So as a powerful tools in representation theory. So for instance, they appear in a crucial way in the proof of the so-called monster-Mondschein conjecture formulated by Conway and Norton. So in the proof of the monster-Mondschein conjecture. So the monster group is, so this conjecture relates an unexpected, this gives an unexpected relation between the monster group, which is the biggest simple sporadic groups, so something in the theory of finite group, and modular functions, so something rather in number theory. And vertex algebras appears here in a crucial way in constructed representation of the monster group. So vertex algebras appears to build representation, infinite dimensional representation of the monster group. So in fact, the representation that appears here were constructed by Lepofsky, no, Frenkel, Igor Frenkel, Lepofsky. No. So more generally, vertex algebra are prominent in the representation theory of infinite dimensional Lie algebras. So infinite dimensional. So in particular, Kac-Moody. Affine Kac-Moody Lie algebras. So I'm not going to talk about this specifically, but we will encounter many examples from this setting, many examples of vertex algebras from this setting. So more specifically, we will see many examples that are actually representation of such Lie algebras. And we will see also related constructions. All right, so this is the first aspect. And remarkably, vertex algebras also appears in string theory as Carroll algebras of two-dimensional conformal field theory. So also appear in, let's say, in string theory. So actually, they give the rigorous mathematical definition of what physicists call the Carroll part of four-dimensional conformal field theory. So to summarize, they correspond to the two-dimensional conformal field theories. So, and this was intensively studied about the same period by Belavin, Polyakov, and Zamolodchikov. So this was two aspects of the theory. And the most interesting thing is that many problems on vertex algebras comes from physics, and conversely, physics usually exploits mathematical results. But even more interestingly, a recent discovery which go back to the work of Nakajima, in the 90s, is that vertex algebra also appears in higher dimensional conformal field theory. In several ways, in higher quantum field theories, so in several ways. Don't explain for the moment, but in this context, the notion of associated variety is a very important invariant. So this is a geometrical invariant of a vertex algebra. So as the title suggests, I will talk about this, maybe not tomorrow, but maybe the day after tomorrow. So this is some geometrical invariant simpler to study than the vertex algebra itself, which capture many information about your vertex algebras. And in this context, it's important because sometimes it gives a mathematical definition of some invariant or observable for physicists, let's say observable, in physics, such as Higgs branch or Coulomb branch. So this is useful in this story, but also it is of independent interest to study representation theory of such algebraic objects. Okay. So this is some motivations to study this, and what is the plan of my lectures? So the plan is the following. So I will start by vertex algebras. So today I will hope to reach the definition of vertex algebras and to give you some first examples, interesting examples. So definition and example. And then I will talk about more geometrical aspects. So I will talk about associated variety and also arc spaces. So these are geometrical objects associated to vertex algebra. So in this way, we go to the commutative algebras world. And finally, I will talk about quasi-Lie, whatever it means, vertex algebras and application. So quasi-Lie vertex algebras are some vertex algebras for which the associated variety satisfy a finiteness condition. So I will explain this, but what is important is that this is a very rich class of vertex algebras that I will focus on, and I will give applications. So I will try to explain some problems motivated by physics where associated variety play a crucial role. This is the idea. All right, any question? So I start with vertex algebras. Tell me if I don't write big enough, and don't hesitate to ask questions. So to start with, I would like to start with an illustrating example. Relatively easy. So let's consider the polynomial algebra with infinitely many variables, x1, x2, etc., with endomorphism, the following endomorphisms that I define as follows. So Hn is defined like this for any integer. So it's just a multiplication by x minus 1 if n is negative. Okay, is 0 if n is 0. And it is n times the derivative with respect to xn if n is strictly positive. All right, so this is an endomorphism which acts on H. And then you can compute the commutators. And you easily observe that this is n times the Kronecker symbol here times the identity on H. All right. So what does that mean? It means that H is a representation of the following infinite dimensional Lie algebra that I denote H at. Defined as follows. So with following the bracket. So 1 here is central. And the commutator between power like this is just that. Right? So you can write also the commutator more globally. If you have two Laurent polynomials here, this is just the residue of f prime t times 1. All right. Where the residue is just the coefficient in minus 1. And how I say that it is a representation, you just consider the assignment. You just send Tn to Hn and 1, the central element, to the identity. All right, so this is obvious that this is a Lie algebra morphism. Okay. So now, I cannot cross. So now the idea of vertex algebras is to encode all these endomorphisms into a single series and to understand more globally this Lie bracket. So idea. So the idea is to introduce the following series. So for some reason is minus n minus 1. So you can say that Hn in this notation is a residue of Zn times your series if you want. But you can also just think it's a notation. And so this belongs to, this is an endomorphism of H. So a priori, this belongs to this. To this vector space. And now I would like to understand the bracket, just a single bracket with these two series. So here I put two different variables. So you think of this in the vector space of Laurent polynomial series with value in and H with two variables. All right. All right. So now I can compute. So just a formal computation, but suppose you have nothing new. I use a Lie bracket here. Sorry. So now we know that this is this. So I have a single sum. This. All right. And then I can write this as follows. this is a derivative with respect to omega to some function that I will function or series times identity. So what is that? So where? This is called the delta function, but the term function is not very good because it's not really a function. Anyway, the definition is just this. Okay, so how to think of this series? You can interpret it as the expansion of the meromorphic function 1 over C minus W in different domain. So let me explain this. So to understand this, maybe I split the sum in two parts. So there is positive n here, and then the negative. But you see this, I can see it as the expansion in this domain. Okay. So when I write this, this means expansion of the meromorphic function given by that. So indeed, let me explain this, and then and then here I have the same, but in this domain with the sign minus. So let me explain this. So you see, if you write this in this domain, you can write this is for n positive, sorry. Yeah, I want Z to be greater. Yeah, this is good. And then because I am on this domain, you can write it like this. Yeah, and you get the correct. Okay, and similarly, you can expand on the other domain. All right. So you can interpret it like this. And so in conclusion, you see that this Lie bracket, you can think of it as the difference between, now if I derivate, I have power 2. You can think of the difference, but expanded in different domains. This is how you can see. But more interestingly, now you can observe, because these are morphism of commutative algebra, you can observe that if I multiply this by Z minus W power 2, this is 0. So you see, it's not commutative, the Lie bracket, but up to some power of Z minus W, it became commutative. In fact, more generally, if you multiply this by the nth derivative of the delta function, you get 0. So maybe I put this because it's all right. Is it okay, Arun? You look. Yeah. If you derivate by omega, just formally, you get n omega n minus 1. So it is what I get. I should put n, but it's yeah. Just so everything is basic so far, but this leads me to some definition, first definitions. So a field. First of all, I want to introduce the notion of field over a vector space V, say V, is a series that I write as before, like this, where AN are endomorphism. V, such that if you apply this series to any element of V, so I mean by that you apply an N to V. Is it okay? Yeah. Then this belongs to this. So in other words, there is only finitely many negative terms. So in other words, they exist positive integers such that A and V is 0 for n greater than. So, and the second notion that that appears here, two fields maybe I did not by FZ the set of fields. I say to be local to each other, if they satisfy such condition, but where you can allow a bigger power. Are local if they exist n such that and of course n depends on A and B. All right, and this has nothing to do with the n here, but you understand. So example, we have seen only one example so far, but HZ is a field on H. This is easy to check by the definition. And HZ is local with itself. So we have already seen that. Huh? Okay. Yeah.
We would like to have some negative powers of Z also there. AZB.
Sorry? Here?
AZB, yeah.
What does that mean?
So it belongs to E double bracket Z. So negative powers of Z also.
Yeah, I allowed. Yeah, this means that so this means this is as a series with only negative power in Z, only finitely many. Yeah, but now observe that the negative power here corresponds to the positive term. So you can translate that they are, for n big enough, this is 0. Is it okay? Yeah, it's just this matter of notation. Which is... All right, so now I would like to, so this will be one of the axioms of the vertex algebra, not in the definition I will present, but you will see after. So this condition is very important. And that's why I started with an illustrating example. In fact, it's not easy to understand this condition because the first time you see this, you should be surprised that it's not commutative and you have this kind of multiplication. So this condition is actually hard to understand, but you can interpret it slightly differently. In fact, this is equivalent to the fact that the Lie bracket here is a linear combination of such things. So in fact, let's say this condition star, in fact, star is equivalent to the fact that this Lie bracket is a linear combination. So in fact, I can mention exactly, you stop at n-1, All right. So this is not so trivial to show. I am not going to prove that. Let's refer to Kat, our draft book with Arakawa, which is on my webpage. It is very drafty, so but at least this is explained. But one direction is easy. This part is clear. From the observation that when you multiply here, you get 0. So one side is easy. The other side, you have to write down the things. It's not so hard, but you have to use this tau function to understand. All right, so this is interesting because it gives you many information, in fact, this writing. And I should also mention that an important fact is that these are also fields. Not only series. So, in fact, physicists write like this. So this is just a notation, but very useful notation. And this is what we call OPE, operator product extension of this product. So what does that mean? In fact, this gives you the singular part. I mean by that with poles in Z is equal to W of this product. So it's just a notation, but not only. In fact, the real thing is that this is equal to that, where you have to put instead of this tau of something, plus something regular. I will discuss on this later. For the moment, just consider this as a notation. So just think this means that. The notation include, if you want, you can, I can rewrite this. But if you want more flexibility, you can even remove, because in fact, the fact it stopped at some point comes from the fact it's a field. It's local, sorry, it's local. But otherwise, you need to precise that it depends on A. But it became 0 anyway from the, of course, it's only for local fields, this notation, mutually local fields. So what I want to say is that this is a kind of replacement of the Lie bracket in the sense that this gives you, so this or this, it's equivalent to the fact that you can compute all Lie brackets. So in our example, it's clear because I computed the bracket from this. So more explicitly, this is something like that. It's not so. So here again, you can stop, but it stops anyway. It's finite sum. And then here you have Cj m plus n minus 2. So I have to mention what it means here because here you allowed negative. So it's just m minus 1. So it makes sense even if m is negative. All right. So let's say that Cj is a product, it's just a notation again. Okay, and explicitly, this is the residue of this, where I multiply by what I want. This is to say J. All right, so this is for n positive. All right. If you look at this formula, you recover Cg by applying this, and you want to denote it by that. But now you can also define when n is negative, so it's slightly more complicated, but you can also make sense using the tau function. So it's again the residue, but here you just have to take tau of the same thing. Oh, sorry, I put n here, so it's n. Then here it's n. Sorry. Yeah, here it's correct. So you take the same things, and then you do the same with this part. So then you can make sense to the nth product also for negative term. And, no, I can't. So then you can, I leave at exercise, you can compute for particular cases. So exercise. So what is this product? Sorry. Good. So then this product is not so, yeah, maybe I introduce giving the definition. It's something like that. And so what is A z plus and z minus? This is just you term all positive term. So this is n negative. So this corresponds to the positive term, and this one is for n positive. So why we have these strange things and why it's important? So this is what we call usually the normally ordered product. And this is again just a notation. But where does come from this product? A remark is that in general, if you do just a naive product, this does not exist in general because it may have infinite terms, all right? So not well defined in general. But this is a good replacement. So it's neither associative nor commutative in general. We will see it become in some portion, but at least it gives you something which makes sense. At least it's well defined, and you can check as exercise. It's exactly the -1 product. Another interesting particular cases of this product is when you apply the field to the identity on your vector space. And then you can check that this is 0 if n is negative. Sorry, I have to put -1 then. -n, sorry. So it's a 0. It's only non-zero when this is negative, okay? And then you get the derivative of your field. It's n minus something like that. So in particular, you get that the derivative is also can be expressed as a product, -1 product. All right. So and now I have introduced a notation. Also, it makes sense to consider this. This is always well defined, but you can also define similarly the normally ordered product by replacing by b omega. And then I can explain a little bit more the notation of OPE. In fact, this is the singular part. So essentially the one given by the bracket, except that you have to take tau plus the normally ordered product. So this is exactly the regular part that does not appear in the notation. You don't need to understand the bracket. Okay, so maybe I finish with one lemma, and then I go to the definition of vertex algebra. So, which is usually attributed to Dong. It's usually referred as Dong lemma, which says that if you have three mutually local fields, so including local with themselves. Then the derivative of z, yeah, I can do more generally. Then in fact, the nth product with the first two, if you want, and z are still local. Okay. So in particular, because of this, you see that the normally ordered product and C are still local. The derivative of AZ and other fields are still local. So it's preserved under derivative and normally ordered product. So one thing I will do today, but maybe after the definition, is that to explain you how to deal with these OPEs. Because as you can expect in practice, you have to understand how to compute OPEs. So this is something, of course, you can use computer when you understand well, but this is something you can do. So let me just mention that the only example we have seen so far is that if I write like this, now I can say that we just have this. This is equivalent to the formula we have obtained. And what it means is it means that the zeros product is 0. And this is just identity. Yeah, sorry. All right. And now we can construct more examples from that one. So I will explain later. One can construct more example. So I give the example and I will compute later. So for instance, let's consider LZ to be half of the normally ordered product of that. So an exercise, so I put the exercise now and we will see whether we have time to explain. I would like to understand OPEs of that. So how you do? You start with OPEs with this. And then you have to use many properties that I haven't explained so much for the moment, but you can do it. And we will see later how to. Okay, so now it's time to give a definition of vertex algebras. Is it okay so far? No? Any question? No. Yeah, I mean pairwise, yeah. Yeah, sorry, I haven't introduced mutually local. Yeah, so when I say that, I also include A within itself. Because you have seen this is not automatic. This is the first example. Yeah, so second part, let's discuss about the definition. So I'm going to give a definition which is not the most usual one. So the following definition is due to De Sole and Katz. And I like this definition because you will see that from this definition, it's easy to give you example. Because otherwise, with the usual definition, you cannot give a single definition after some time. So the definition I give is the following. So a vertex algebra is a vector space V equipped with a distinguished vector, usually denoted like this, which is usually also called the vacuum. Non-homomorphism, T, which is usually called the translation operators. Translation operators. And a collection of fields, of mutually local fields. And the set of mutually or pairwise, I don't know what is the best terminology, fields S on V. So you see, they are mutually local, but also fields, it's already an axiom. You ask this, such that, so you have some axioms. You ask first that T applied to the vacuum is 0, and the bracket of T with the derivative of any fields in S is, with AZ is the derivative of Z for all fields in your generating set. And second, you want that V is generated as a vector space by the vectors of this form, like this, where, so for I, J, sorry, these are fields. These are elements of your generating fields that I write as usual, like this. So in other words, it's generated by what we call the Fourier mode, so the endomorphism associated to your series applied to the vacuum. All right, you can add the vacuum, but it's not necessary because vacuum should appear. So one remark is that this is equivalent with this notation to the fact that T, so this is an endomorphism of N, of V, and this also. So the commutator between these two endomorphism is minus N, A, N minus 1. This is maybe more explicit. And in this case, we say that V is generated by the set S. Okay. So with this definition, we have at least one example. So example, with VH as before, and S, the set just consisted of Z, of HZ, and I take for vacuum the identity. And for T is determined by in fact this condition. So maybe you can show that explicitly. You can explicit here what is T. It is, if I am correct, this. Okay, and you can check that it satisfies the axioms. Okay, and we will see another example coming from L later. So I would like to discuss some consequences of the definition. So first consequence is that if you apply AZ to the vacuum for all fields in the generating set, then this belongs to this. So this time there is really no negative term. Before there were only finitely many, but here it's a real formal series with only positive term. Yeah. Sorry, here. Yeah. Yeah, you're right. Yeah, this you can, yeah, this is H, N, H minus N, HN. Yeah. Yeah, this is something interesting because, yeah, I realize I'm slow, but it's fine. Here, I will describe the OPE. For those who know, we will encounter the Virasoro relation. And in fact, T is exactly, I haven't explained, so maybe it's better I explain what I wanted to say with LZ. But T turns out to be one term of this part. And so this is interesting because it says that it has a richer structure, what we call conformal. I'm not going to explain, but this is a very good remark. You can write it more symmetric way. Yeah, using this. Sorry? Yeah, I forgot. This is HN certainly. And so, yeah, so N is here. And this is, yeah, there is a shift. Yeah, maybe. Yeah. This is what you say? Yeah, there is a shift. Yeah, thanks. Yeah. Yeah, maybe I did a mistake somewhere, but I think this is correct. Let me check. This is what I get. So anyway, we will come back, but I think this formula at least is correct. Yeah, and then I think this is, yeah. So yeah, I want to explain what I was to explain. Yeah, I want to explain this. Yeah, so how to prove this? I'm not going to prove many things, but at least I can explain this. So remember that this is a field. So in particular, there is some M, let's say, that this is 0 for n strictly bigger than m. Yeah. And so I can choose m, or I assume that this field is non-zero, otherwise it's not interesting. And let's assume that m is minimal for this property. All right. I want to show that m is smaller than 0. It cannot be greater than 0. So now apply both sides of I forgot where it is, here to the vacuum. So you have T A N to the vacuum, which should be this. So maybe I put directly M. So what is this? This is T applied to the vacuum plus this. All right, but by the translation axiom, this is 0. And by the choice of M, this is 0. All right? So this means that this is also 0. But now you see that if M is strictly positive, then you get that this one is also 0. But this is contradiction because M is minimal. Okay, so this is very easy to see. And in fact, because you can view V is also generated by, I haven't explained the notation. Okay, so let's, yeah, maybe I introduce one more notation is that, one more notation is that, let's consider, so you have a vector space, let's say W, and you have a set as before a local field, mutually local fields. And I denote by this the subspace of the set of fields over V generated by all fields obtained by successive applications. So I just write application of nth product from element on in S. Plus you add the identity. So what does that mean? You take all fields you have, you consider all nth product you want. By Dong's lemma, it remains pairwise local. And then you take this and you take the space generated by that. All right? But of course, a vertex algebra is a vertex algebra also generated by this, a fortiori. So this lemma also holds for all fields in this bigger fields. All right? So another thing I want to say, I'll leave at exercise. I want to give slightly more properties. So because of this lemma slightly improved, we can define the map from this new subset of fields to V, sending a fields here to the limit of your field applied to the vacuum. So if you want, this is just you evaluate as z is equal to 0, because now there is no negative term. So this makes sense. And what is the aim? I hope to reach at least this today, is that S is an isomorphism as vector space. This is a so-called state field correspondence. And thanks to that, I can give you a more usual definition of vertex algebra. So this makes sense? Is it okay? So I leave at exercise some properties. Exercise, first thing you can show is that if you apply to the nth product, this is really nice, but you get A. I will say what is A, but you can guess. I just set where A, I just set the image. Okay, so you get this. Yeah. And second thing you can show is that S of the derivative of a field, it is a translation applied to A. Again, A is a limit of the field at 0. So another interesting thing is that you see that again, this belongs to this. So this means that you can write like this. In fact, you can write something like that. And you can explicit what is this. In fact, it's a consequence of the second exercise. Yeah? So V a priori it's a vector space. Here. This is an element of V. A is by definition the image of that. So now maybe I can mention, in fact, here you get explicitly this. Because remember that it's an endomorphism, but applied to the vacuum, which is an element of V. So this belongs to V. Okay? The product here is defined for, the notation is confusing, but because at the end it will be the same. But here, this is a product I define for fields using the residue and blah, blah, blah. And you can, in fact, explicit the formula. Here, it's a bit different. A and B are elements of V. And this is the endomorphism that appears in your series applied to B. So, of course, the notation is voluntarily confusing because at the end it will correspond. So this is, but it's true that at the beginning you have to be careful. One is just an endomorphism, the other one is an end product in between fields. Yeah. Yeah, so, so here what I want to say is that you can explicit this. It's essentially an induction from that. But this is, in fact, T n, so n times the endomorphism applied to A. This is exactly that. So the purpose is that for all AZ in your generating fields, and you can even extend to that, you have that AZ 0 is just this series. All right, so maybe I don't explain that. So now I can just state the fact that it is an isomorphism. Ah, yeah, sorry. Yeah. You can think of exponential ZT Well, anyway, just remember, yeah. Yeah, I think this is correct. Yeah. Here I change. Because I want to emphasize positive term. So this is not, this is a good remark. This is in fact A minus N, if I am correct. Yeah, it's this one. If I am correct, it's something like that. Is it okay? No, so you remember that the convention is minus n minus 1. So this is A minus n minus 1 applied to vacuum. Yeah, minus n minus 1. No? Is someone agree with me? Yeah? Okay. Yeah, so because it's a time, I just mentioned one theorem. So S is an isomorphism. So linearity is clear. Surjectivity is clear because A, I already mentioned, so thanks for your question. This is this. So I already mentioned this is S of that. So this means any element of V can be written as the image of someone is in S. And for the injectivity, you need to use that. But imagine this is 0. Sorry, this is 0. Then you see from that formula, that formula, actually, this is 0. Okay. And now I would like to explain the proof because it's the only moment I want to use the locality to prove something. So now, hence, for any fields in your generating set S, you have by locality, you have some equality like this. So let's say, yeah. Okay. So now let's apply, sorry. Okay, so now let's apply to your vacuum. So this is 0. And then I take now, is it okay? No? Yeah, it's okay. So now I take the limit at W. If I evaluate at W is equal to 0. So evaluating at W is equal to 0, I get that AZ of B, I can write like this, is 0. All right? Because this is exactly the definition of the function, the map S. But this, by the surjectivity of S, this implies that your field is 0. Because applying to any vectors, it gives 0. So this is a so-called state field correspondent. And so I conclude, can I have 1 minute? Yeah, I just conclude with properties that this gives you. And then this leads me to the usual, as in Katz books, for instance, or Frenkel-Benzi books, definition of vertex algebras. And tomorrow I will focus on examples. Tomorrow it will be devoted to examples. So consequences, you can define a map. So this time from V to the set of fields over V, sending a vector to some fields. So that I defined, of course, by the converse image of A. I write it as usual, like this. And now you have the following properties. Okay. So you have that the fields associated to the vacuum is just the identity. And moreover, for all A in V this time, you have that this field applied to the vacuum belong to that. Okay? So this is clear. Second thing, so this is usually called vacuum axios. You have also we recover the axiom about the translation. So you have more precisely, you have this, we have already seen. This is a derivative. But this is also from what we discussed before, the fields, associated to T applied to A. So you have a new relation. So these are usually called the translations axiom. Then, of course, you have the locality. So Y AZ and Y BZ are local. So for all fields associated to V. And last things, so now there will be no anymore ambiguity. The nth product between two fields is a product, is the field associated to the nth product. So if I do that, so the notation was good. If you have a vertex algebra, it means exactly that, all right? And we'll discuss tomorrow, but this identity leads you to the famous Borchardt identities that can be seen as Jacobi or associative identities for vertex algebras, which are neither associative nor commutative in general. So, okay, sorry, we devote 1 hour for the definition, but tomorrow we will see more interesting examples, non-commutative and also commutative. And then on Wednesday, we start geometrical part. Yeah. Thank you.
Comments? If not, let us thank speaker again.